All right, chapter 2, we have polynomial and rational functions, and this first section is talking about quadratic functions. So what we'll look at is analyzing graphs of quadratic functions, writing quadratic functions in standard form, and using results to sketch graphs, and then finding minimum and maximum values of quadratic functions in real-life applications. So the graph of a quadratic function, well, first, the definition of a polynomial function. So this is something that you need to know, is that for a polynomial function, your exponent, your n value, so if you notice these are all your n's, whatever your exponent is, has to be non-negative, which means that it has to be greater or equal to 0. So if you see what you would think maybe would be a polynomial, but it has a negative exponent, it's not a polynomial. So that's one of the keys. When you have a polynomial, your initial value obviously can't be 0, and so you would have some constant and then x to at least the 0 power, and then it would count down from there. So polynomial functions are classified by degree. For instance, if you have f of x equals a, where a is really a constant, that would be like saying f of x equals ax to the 0, right? Because anything to the 0 is 1. So f of x equals a constant is a polynomial. It's just called a constant function, and it has a degree of 0. If you have a line, the mx plus b, it would have degree 1, since this degree with your x is 1, and that would be a linear function. So again, talking about that line, mx plus b, you have a slope m and an intercept b. But then in this section, we're getting into that second degree polynomial, which is your quadratic. So with your quadratic function, you have your ax squared plus bx plus c. So whenever they ask you to write that quadratic function, you have an a, a b, and a c value. So the graph of a quadratic is a parabola, which hopefully you're pretty familiar with, and the idea that parabolas occur in many real-life applications, especially those involving reflective properties such as satellite dishes or flashlight reflectors. All parabolas are symmetric with respect to a line called the axis of symmetry. So your axis of symmetry is the axis where if you were to fold your parabola in half, it would fold onto itself. The point that the axis intersects the parabola is the vertex. So if you had a parabola and this was your vertex, your axis of symmetry, or sometimes we'll just say the axis, your axis always goes through the vertex. So here's your basic characteristics of quadratic functions. If your a value is positive, your parabola will open up. The domain is always all reals. Oops, that was supposed to be highlighted. So your domain is always all reals. If you just have your ax squared, your range is 0 to infinity. It's intersecting at the origin. And then you have your increasing, decreasing. It would be even because it has that reflection symmetry across the y-axis. And that axis of symmetry is the equation x equals 0, which is your y-axis. And that minimum or your vertex would be at 0, 0. So then if your a value is less than 0, your domain is still all reals, but this time your range is negative infinity to 0 since your parabola is opening down. It's still an even function. You still have that same axis of symmetry and that same vertex. So your general quadratic form is ax squared plus bx plus c, where the leading coefficient a is positive. Again, if a is positive, the parabola opens upward. When a is negative, the parabola opens downward. And then in a couple examples here, we will look at finding the coordinates of the vertex. So for this first example, just the idea of sketching the graph of these functions and comparing them with the graph of x squared. So first, if we were to sketch x squared, it would be at 0, 0, and then that 1, 1, and then 2, 4, and then we would have that reflection, right? So that y equals x squared would look like this. And so if we were to sketch negative x squared plus 1, we know that this is going to open down since the a value is negative, and then this plus 1 is going to shift up 1. And so if we were to graph that, we would shift it up 1, but now it would open down. Right, so that graph would look like this. So it has some of those transformations in there. If we look at b, this plus 2 is going to shift to the left 2, right? Because it says it's going positive 2, but we really know it's going opposite. And then it's going to shift down 3. That's this minus 3. So if we take that vertex and we go left 2 and down 1, 2, 3, we're at that point. And our a value is out front. It's a 1, so it's positive, so it's going to open up. And then we could sketch. So we go over 1, up 1, and then over 2, up 4. And then you could sketch your parabola through those points. Okay, so standard form versus, if we go back, remember that this was called general form. So your general form is ax squared plus bx plus c. But standard form is a times x minus h squared plus k, where the vertex of the parabola is the point hk. So in standard form, because you have this, oops, I don't want to do that. Because you have this h, trying to highlight it, and this k, we could actually figure out where the vertex is when we're in that standard form. So it can be really helpful in graphing this. Now, in order to identify the vertex, we have to put this into standard form, which is going to require us to complete the square. So to complete the square, we're going to keep the f of x, and then we're going to group this part with the x's together. And we need this x to have a leading coefficient of 1. But before we do that, we're just going to group our 2x squared plus 8x. And then our plus 7 is going to just stay separate. So then what happens is we need this inside part right here. This is what we're going to try to turn into a perfect square trinomial. So in order to do that, we have to factor out the 2 because we need the x to have a leading coefficient of 1. So we have x squared plus 4x, and now we're going to have to do something with this. So in order for this to be a perfect square trinomial, we need to add our b over 2 squared to it, which means if we add b over 2 squared, then we also are going to have to subtract b over 2 squared, and then we're still going to have plus 7. Okay, so because we're adding something, we also have to subtract it, so that way we're not actually changing the form. So if we look at this equation, if we consider this to be like our a, our b, and then this would be our new c value. So our a is 1. In this case, our b is 4. So when we're adding that in, we're going to say f of x equals 2 times x squared plus 4x plus 4 over 2 squared minus 4 over 2 squared. So that way we just keep it the same, plus 7. So we'll have 2 times x squared plus 4x plus 4, and then minus 4 plus 7. And we want these parts to be grouped together out here. So that way we keep this part right here as a perfect square trinomial. So what happens then is we need to factor that. And if you factor a perfect square trinomial, it will factor, if you think about it, or if you try to just go through factor, it factors into x plus 2 times x plus 2, and then you have plus 3, which you could write it as 2 times x plus 2 squared plus 3. So now this is in that standard form, which remember was your f of x equals a times x minus h squared plus k. And so if we need to find the vertex, we need to look at the h and the k. So in this case, our vertex for this parabola would be negative 2, 3, and it would be a parabola if we had to describe the graph. Because the 2 is positive, it would be a parabola opening up. All right, if we look at the next example, again, we're describing the graph and identifying any x-intercepts. So let's go through that process again of finding the vertex. So we have f of x. We're going to group the x's together. So we'll have a negative x squared plus 6x, and then the minus 8 stays on the outside. That's going to give us part of our k value. So remember that x needs to be positive. So we're going to factor out a negative, and so we'll have x squared minus 6x. So this is negative 6 is our b value. And so we're going to add b over 2 squared. So we're adding 6 over 2 squared, which means we have to subtract 6 over 2 squared and then minus 8. So if we start simplifying, we get negative x squared minus 6x plus 9 minus 9 minus 8. So we get f of x equals negative. This will factor into x minus 3, x minus 3. It always factors into the same two factors. So you should never have two different factors, because what happens is that's what gives you that square, that x minus 3 squared minus 7. So if we were describing this, this would be a parabola, right, that opens down. Since our a value is negative, it would have a vertex of 3, negative 7. And then to find the x-intercepts, we actually need to go back to our original equation. So we'll leave a spot here for our x-intercepts. But when we go back to f of x, we're going to factor this to get our x-intercepts. And to factor a quadratic, it's always easiest to factor it if your leading coefficient is positive. So let's factor that negative out. You have x squared minus 6x plus 8. And so you would get a negative x minus 4 and x minus 2. So your x-intercepts would be when x equals 4 and 2. So your x-intercepts would be at the point 4, 0 and 2, 0. Again, that negative is still out front because you have that parabola that's opening down. So if you want to find the maximum or minimum values of the parabola, you're really finding the vertex. Because remember, with the vertex, if you have a parabola that opens up, right, so if your a is greater than 0, your vertex will be a minimum value. But if you have a parabola that opens down, so your a is less than 0, your vertex will be a maximum value. So the easiest way to find your vertex is you could potentially go and put your function into standard form, where this is kind of the shortcut for it if you want to memorize that a times x plus b over 2a quantity squared plus c minus b squared over 4a, which is really what we did there to complete the square. So the formula for the vertex is the x coordinate of your vertex is the negative b over 2a, and the y coordinate is when you plug that x coordinate back into the function to find your y value. So this is just that slide that kind of gives you what we just talked about there with the maxes and mins. So this next example, it says the path of a baseball is given by a function f of x equals negative 0.0032x squared plus x plus 3, where f of x is the height of the baseball in feet and x is the horizontal distance from home plate. What is the maximum height reached by the baseball? So again, we have this function. It has a negative a value, which means it's going to be a parabola that opens down, so the maximum height will be the vertex. So if we want to find the x coordinate of the vertex, we're going to do negative b over 2a from the a, the b, and the c values. So negative b, we would have negative 1 over 2 times a, which is negative 0.0032. And so if you calculate that, you get 156.25. And so then to find the y coordinate of your vertex, what you do is you plug that x value that you just solved for back in to your equation for x. So you're just finding f of that value. So your y coordinate would be negative 0.0032 times 156.25 squared plus 156.25 plus 3. And if you go through and calculate all that, you get 81.125. And here you go back and we look at the label and we're in feet. And here, up here, we would be in feet. So what that means is your x coordinate is your horizontal distance. So it's going to reach its maximum height of 81 feet when it's 156.25 feet away from home plate.